we invite Dr. Kitanidis, a professor in civil environmental engineering and Institute for Computational and Mathematical Engineering at Stanford University. Dr. Kitanidis is one of the world leading experts in ground engineering and hydrogeology, and he has had significant contribution to several important areas in hydrogeology, like the study and analysis of groundwater flow and reactive transport with the mixing process, and geostatistics, inverse modeling, data assimilation, and uncertainty quantification, and lastly, stochastic optimization and control of the surface reservoir and subsurface aquifer on the uncertainty. And he received several awards from large communities such as AGU and ASC, and was recognized in 1991 as a highly cited researcher from ISI Web of Science. And thank you, Peter, again for accepting our invitation. So feel free to share your slide and start the presentation.
Thank you very much for the invitation and the chance to talk. And thank you, Harry, for the generous introduction. Okay, so our topic is solute dispersion in groundwater, a topic that is related to groundwater contamination and remediation. So first, a little bit of background. Okay, so groundwater is one of the most precious resources on this planet. 98% of the water that is not seawater and is not in the form of ice is groundwater. But it is a fragile resource that is affected by, among other things, groundwater contamination. So we have contaminants that come from industry. For example, here you see a contaminant plume. And you have a source, and then the contaminants are moving and spreading. So this is the problem of transport. You have also contaminants from agriculture. In California, and I'm sure in Hawaii, you have a problem of more distributed nature, pesticides in groundwater. And of course, in all islands, including and coastal areas, you have seawater intrusion. As we overpump the aquifers, the pressure in the aquifer drops, and that makes it easier for seawater to intrude. Also, as we overpump aquifers, we cause lenses of clay that contain, for example, arsenic to be compressed, and that releases other contaminants. So the problem of predicting concentration is a central one. And the question is, how well can we predict solute concentrations? And in fact, last summer, I worked on a chapter from the Groundwater project, a chapter on dispersion, and I communicated with a lot of people and also read a lot of papers. And one of the messages I got, and it came from a distinguished researcher and also with extensive practical experience, is the following. We should make it clear to new hydrogeologists that our understanding and ability to quantitatively predict solute concentrations in groundwater is truly weak and will remain so. We have to accept that fact. All right, so my promise to you today is I will help you appreciate the challenges in predicting solute transport, and particularly in predicting solute concentrations. And also to remove some of the mystery and confusion about the problem of dispersion. In porous media, dispersion seems to be, the usual suspect when something does not work. Okay, so let's look at the challenges in predicting solute transport. By the way, this seminar is at an introductory level because I realize that there may be people who are not working in groundwater and also students who have not taken yet a class in hydrogeology. So the first challenge is that geological media are highly heterogeneous. And in fact, you have heterogeneity at all scales, from the scale of the pore all the way to the scale of the formation. Here we see an outcrop and we can see some of the variability. The second is that geologic media are difficult to characterize. What does this mean? It means that here we see the outcrop, but of course, below ground, we cannot go and see all the heterogeneities. So what do we have? Well, I show a black box for dramatic effect. Of course, in reality, we do know something. We have an idea of what the conductivity overall might be, but not at the level of detail that would allow you to predict concentrations at a point or at a small volume. And the third challenge, that is perhaps the one that is least appreciated, is that mixing in groundwater is extremely slow. And that results in highly non-uniform concentration. So within a distance of a few centimeters, you have dramatically different concentrations. Remember that when you take samples that are, 1 decimeter or a few decimeters, that there is tremendous variability. Now, that's not a problem we have in groundwater flow when we try to predict pressure or hydraulic head. Pressure and hydraulic head tend to spread out much faster. So the result is they become nearly, less non-uniform. But concentration does not spread out quickly, and you have tremendous non-uniformity. All right, so now let's talk about dispersion, which is part of the bigger problem. Let's start with the simpler definition that dispersion means spreading. Okay, so we're talking about the spreading of solutes. And we can see spreading at the pore scale, like here, both in the longitudinal and in the transverse direction. We can have it in a sandbox, the laboratory scale. We can have it in the field where we have plumes that may be hundreds of meters long. All right. Now, what causes dispersion? Well, the answer is simple. It's non-uniformity in flow velocity. That is the primary cause of what we call dispersion. So essentially, what you have is velocity varies, again, at all scales. Here we see some simulation at the pore scale, and you can see that even though the medium does not look anything like a fractured medium, the flow actually looks a lot like it's in a fractured medium. Okay, so here what we plot is the magnitude of the velocity. And you can see that there are paths where the magnitude of the velocity is high. And there are other areas where the velocity is close to zero. So tremendous variability in the velocity. And we have the same thing at larger scales. So at all scales, we observe this variability in flow velocity. Okay, so actually, let me discuss this a little bit further. So why does this cause dispersion? Well, if you have some mass in a high velocity area, and then you have some mass in a low velocity or immobile area, well, this mass will move quickly while this will stay behind. And that increases the separation, and that is the spreading. It increases the spreading. So variability in velocity causes dispersion. So the technical problem of dispersion is that we do not really know the velocity variability. We only have a vague idea of what it might be, but we don't really know the details of how velocity varies, and we don't know what the initial concentration is. So if we did know, we would be able to predict what the concentration at a future time is, but we don't. So the question is, can we estimate dispersion without full knowledge of velocity and concentration variability? Okay, so everything in groundwater starts with column experiments. And what we see here are columns. So you have an inflow point, and then the water goes through a column packed with sand, and it exits here. And here we measure the concentration at the outflow. So we start with clean water, and then at some point we switch to a certain concentration, C0, of a tracer. And then at the outflow point, we measure the concentration. And here are some results. On the x-axis, you see injected volume, which is a surrogate of time. The idea is that the larger the injected volume, the more time has elapsed. On the y-axis, we have the normalized concentration. In other words, the actual concentration divided by the C0, the concentration of the tracer once we start going. Now, if we did not have, if this were plug flow and we did not have any diffusive process, we would have expected that the concentration at the outflow would be practically zero. And then at some point, it would abruptly go to C0. Okay, so this is the time versus concentration plot. Now let's see also the view along the column. So now we see along the column. Previously it was time versus, rather concentration versus time. Here is concentration versus space. So let's think of this as the whole column. It starts at 0 and ends at 1 meter. And here we see the normalized concentration. Now, if we only had advection and nothing else, we would have a step function, the blue line. If we add diffusion, well, diffusion changes things a little bit, okay? In reality, we get something that looks like diffusion, but it's much more than diffusion. All right, so this is the effect of having both diffusion and hydrodynamic dispersion. And hydrodynamic dispersion is the net effect from the variability of velocity. Okay, so for this column experiment, we can say that, okay, we'll use a model that has two parameters. It has a mean velocity, and it has a dispersion coefficient that has dimensions L squared over T. And we model hydrodynamic dispersion as if it were diffusion. Not that it is diffusion, but we use the same Fickian model to describe dispersion. So for the column, it's just two scalars, a U and a D. Now, if we expand that to other cases, we'll talk about that. But for now, we have a U and a D. Furthermore, it has been found that the hydrodynamic dispersion coefficient, in other words, the total dispersion consists of two parts. It's the sum of two parts. The first is called hydrodynamic dispersion, and the second part is the diffusion. Okay, the hydrodynamic dispersion coefficient is U, in other words, this mean velocity times A. And what is A? A is the dispersivity. It is a quantity with, units of length, and it's considered a property of the medium. Now, this is called the Scheidegger parametrization. Parametrization is when we try to relate macroscopic parameters, not parameters at a single pore and so on, but for the whole medium. So this D is a macroscopic parameter, U, the average velocity, is a macroscopic parameter, and A is a property of the medium, also macroscopic. And Scheidegger is the name of the person who 60 years ago was studying it and published on this. Okay, now there are really two parts. The first is the Fickian. Okay, so these first two assumptions, that we have a mean velocity and dispersion coefficient, introduce the Fickian model, and the other is the Scheidegger. So these are two different things. Actually, you could have Fickian with a different parametrization. Or you could have something that is non-Fickian, but has something like the Scheidegger parametrization. Now, in the literature, it's often confused that these two things necessarily go together. It's true that the basic model that we have been learning and teaching for the last 60 years almost is both Fickian and Scheidegger, but in reality, these are two different things. Okay, now let me explain what Fickian means, and for reference, I will introduce the Gaussian plume. So what we see here is a Gaussian plume. X is a location, And here we have a concentration C over C0, and this is the Gaussian shape. It is the smoothest curve you could imagine. And Fickian means that the transport takes place from a higher concentration to a lower concentration, and the rate is proportional to the slope. So here we have the highest rate, while here we have lower rate, here we have 0, and here we have low rates. The Gaussian plume, of course, is a very convenient model. If you start with a Gaussian plume and the advection dispersion equation, the model I described before, applies, you will predict a Gaussian. So the Gaussian begets another Gaussian. So you start with initial condition Gaussian and you get a future Gaussian. And if we start with something that is not Gaussian, it's more irregular, over time it tends to become more Gaussian-like. So overall, a very nice model. But there is one more thing about the ADE and the Fickian. Let's say that spreading is quantified by the second moments. Okay, so what do we mean by that? You imagine that you have an awful lot of particles, solute particles, and they are moving. So you can find the centroid of these particles, the center of mass, and then you can find the mean square distance from the centroid. Okay, so this is what sigma is. Okay, so the rate of increase of sigma, so you expect that sigma will increase over time. That's spreading, that's dispersion. So increases over time. It says that this sigma over dt, in other words, the rate of change of sigma, is constant. And in fact, it's 2 times the dispersion coefficient. So it's very simple. And that is an important, another nice property of the Fickian model. Now, what does it take for hydrodynamic dispersion to be Fickian? The first is stationarity. Stationarity is not an easy concept. What it means is that the bulk properties of the geologic formation do not change with location. So what would be an ideal kind of situation where we have stationarity? Homogeneous sand. Its grain is different, but they all come from the same distribution. And similarly, every pore space is different, but it comes from the same distribution. There are no large scale trends or anything like that. So that's what stationarity is. So certainly in the case of homogeneous sand, we have stationarity. The second is that initial conditions should have negligible effect. What does this mean? Now, if we micromanage the initial injection, let's say that we go to every pore and we decide that we will put all the mass in immobile areas, in immobile zones. Well, in that case, the initial transport rate, the initial advection rate will be close to 0, right? Because it's in immobile zones. And also the spreading will be next to 0. If on the other hand, we put everything, let's say, in the most mobile parts, again, everything will be moving very quickly, but with not much dispersion. So it's obvious that the detailed microscale, let's say, distribution must be forgotten, okay? So it must not have an effect. Okay, it turns out that the effect of initial conditions decay exponentially. So in other words, the effect is proportional to exponent of minus t, t is the time, divided by a characteristic time, tr. So tr, the characteristic time, is called the relaxation time. Okay, so the idea is that if I know the relaxation time, we can compute upper limits to the time required to forget initial conditions. So for example, if t is 5 times tr, then exponent of minus t over tr is a small number, I think something like 1%. And we can say, well, yeah, it has forgotten the initial conditions. Okay, so that's important. All right, so these were the conditions for Fickian. Okay, I haven't said anything about Scheidegger. Okay, so what does Scheidegger mean and how can we place it? I'll try to show you, to discuss this through this cartoon. First of all, I will assume, it's a big assumption, that we do have a Fickian model. In other words, we're talking about a stationary medium and large time result. So Fickian requires, it's a matter of time, requires time, and we have reached that. Okay, now let's say that we have these streamlines, and we also show a profile of the velocity at the neck. All right, so we see that we have a velocity variability both in the longitudinal direction and in the transverse direction. Now, how can we theoretically analyze this? Theory is good at, is best at dealing with extreme cases. So we will look at extreme cases. The first extreme case is that advection dominates. In other words, if a particle stays on the same streamline that it started with without ever jumping off, it would still experience periods of high velocity and periods of low velocity. And at the end, it will experience more or less the whole range of velocities. Okay, so in this case, we might as well not have diffusion. Of course, we always have diffusion, right? There's no way that you cannot have diffusion, but it does not matter. It does not have an effect on dispersion. In this case, we get the Scheidegger parameterization. The hydrodynamic dispersion is mean velocity times A. Okay, so this is the mean velocity multiplied by a coefficient that is characteristic of the whole medium, not just a location here, but a whole medium. All right, so this is the advection or velocity dominating case. Since we looked at one extreme case, now let's look at the other extreme case, okay? What is the other extreme case? The other extreme case is that if a particle stays on the same streamline, it will never see another velocity. For example, if you have parallel flow, so the velocity is constant on each streamline, well, you start with a velocity that is, I mean, if the velocity is high here, it will be high throughout. If you experience some variability, it will have to jump streamline. So now diffusion is important. In this case, mass transfer dominates. We say that mass transfer dominates, and it turns out that the correct parameterization for this case is that the hydrodynamic dispersion is equal to the mean velocity squared divided by K. And what is K? K is another macroscopic parameter of the medium, just like A is. K has dimensions 1 over time, and we can call it a mass transfer coefficient. So U squared divided by a mass transfer coefficient. Now there are media for which you expect that if it was perfectly stratified, or you expect that, for example, in fractured media. In fractured media, once something gets in the immobile zone, the only way to get out is through diffusion. Okay, so you expect to be closer to this. Okay, so these are the two extreme cases for which theory gives an unambiguous answer. Now, in the real world, you expect that both matter, right? So in this case, theory can go that far. You can say that one parameterization that makes sense is U times A, so the same things, times a function of this dimensionless parameter. This is a dimensionless parameter. If you spend some time, you'll recognize it as a Peclet parameter. So it's a dimensionless number. It's the U, the average velocity divided by two macroscopic parameters, K and A. So the best we can do in this parameterization is we need two macroscopic parameters, and in some cases, three. And it turns out that this is a good parameterization, except that if you look at the literature, which one has monopolized all the attention? It's this one. Now, there are good reasons for that, as I will explain, but essentially, it's not that everything has to follow the Scheidegger parameterization. Okay, so how good is ADE, the advection dispersion equation, the one that has one velocity, one dispersion, and it tries to represent solute transport over a whole domain? Okay, so it works well for reproducing breakthrough curves in columns that are long enough, well-packed, and homogeneous, and with homogeneous material. Notice that I put some qualifications. Long enough, often columns are not long enough. Well-packed, well-packing is really difficult. And with homogeneous material, sometimes the material that is introduced is not well mixed and it's not homogeneous enough. Now the ADE is so appealing and so easy to use that people have been using it for field applications. In other words, they have a model that has one velocity, except that the velocity now is going to be a vector, right? Because it has components in all three dimensions. And the dispersion is not going to be just one scalar. It's going to be a tensor. But that means that you have one dispersion coefficient in the longitudinal direction, in the direction of flow, and this is known as the longitudinal dispersion. And another in the transverse direction, transverse to the flow direction. Okay, but basically it's the same model, except it's applied in 2 or 3 dimensions and it's supposed to be for the field. Okay, now I will look at relatively homogeneous and highly heterogeneous media. So let's stay tuned about to see whether it works. But before I do that, I want to show you this plot that is from Gelhard et al., 1992. It's an interesting plot. There are many questions, of course, on how the exact details were derived, but it is an interesting and important plot. So what do we have on the x-axis? On the x-axis, we have the scale of the field case or experiment. And what does this mean? Well, it's a complicated issue, actually. But to make things simple, let's say this is the size of the plume. So you have plumes that are small, let's say 10 meters, like here. And you have plumes that are large, 1 kilometer to 10 kilometers. You can have really large plumes. Okay, so, or it could be the size of the domain over which you do the experiment. Okay, so you got an idea of what the scale means. And on the y-axis, we have the longitudinal effective dispersivity. What does this mean? Essentially, it is an effective dispersion rate, the rate at which the second moment increases in time, normalized by the velocity. Of course, it's affected by the Scheidegger kind of thinking. You know, it's what people feel that is appropriate. But in any case, this gives you a measure of how rapidly a plume is spreading, okay? So again, it is the effective dispersion divided by the mean velocity. And we see that you get quite large numbers. In the laboratory, you expect to get what? Millimeters for this quantity, the effective dispersivity. The effective longitudinal dispersivity is millimeters. But here we see for a plume that is 1 kilometer, we can have a dispersivity of 100 meters. That means that large plumes tend to spread faster. And that is a good thing in a certain context, right? Because the more they spread, the more dilution of contaminants you get. And that is usually a good thing. But it has kind of confused people who think, oh my God, it seems like the dispersion coefficient I should be using depends on the size of my plume. Okay, so let's focus. We don't have much time, so I will focus on two field studies, famous ones. The first is the Borden side, and the second is the Maid side. Okay, the Borden side, Borden is in Ontario, Canada, and there was a study done in the early 80s. People from Stanford and University of Waterloo worked on that, quite a few people, like Professor McCarthy and Cherry were leading, and several people from Stanford, like Freiberg and McKay, and many students that went on to distinguished careers worked on this project. All right, so the variance of low conductivity is 0.29. I will explain that. The other experiment was some years later, maybe about 15 years later, the MAID side. MAID stands for macro dispersion experiment. Macro dispersion actually means dispersion at a large scale, at the scale of a plume, for example. All right, and the variance of log K here is 4.5, much bigger. All right, I need to explain these numbers because they may not mean much to you. So first of all, what does variance of log K means? Imagine that we have a lot of samples and we measure the conductivity on each sample. Of course, the scale of the sample matters, but let's assume it's some reasonable scale. And we take the logarithm of the measured values and then we find the variance. Okay, so it's a little bit more complicated than that, but that's good enough for now. Now the difference between 0.29 to 4.5, should we be impressed? Now let's think in a different way. Let's talk about the range of conductivity values. So now I'm throwing out the top 1% and the lower 1%, and that leaves us the 98% range. And I take the ratio of the largest to the smallest. So it's like thinking, oh, what is the range of values that you get at Borden versus MAID? Well, at Borden, 12, at MAID, 22,000. So it's a very dramatic difference, right? These are two very different cases. All right, so let's look at this picture that is from Borden experiment day 381. We have a vertical cross-section along the center of the tracer plume. Okay, so at the top, we see the actual one. Well, actual in the sense that we had a lot, they had a lot of measurements, and through interpolation, we get the isoconcentration lines. And it's quite irregular, as you can see. And below, we have a model or idealized case that is similar to the one at the top in three important ways. So you have a three-dimensional plume. Here you see cross sections, but the analysis is for three-dimensional. Okay, so the two plumes have the same mass. So if you integrate concentration, you will get mass. They have the same mass. This and this, they have the same mass. They have the same center of mass, centroid. They have the same centroid. And also they have the same second moments. So even though they are the same in these important ways, they are not the same in terms of concentrations. And in particular, you see at the edges of the plume, significant differences. Okay, another important feature that you see universally is that the peak value in the real thing is higher than the peak value in the Gaussian plume, the idealized plume, which means that the Gaussian or idealized plume tends to overestimate dilution. All right, so this is an important feature. The other, again, I mentioned already, at the edges, of course, at the edges, both tend to go to zero. But if I take the relative difference, in other words, the difference here versus here, and then I divide by, let's say, the actual one, it turns out that as I go further at the edges, this error or this difference increases in absolute value. In other words, that means that in relative terms, it's practically impossible to predict using this model the concentration at the edges of the plume. Okay, so the fact that the actual plume is not Gaussian has caused a lot of concern. People say, oh, that means that the ADE is wrong. Well, it turns out, though, that it's all a matter of scale. Okay, so yes, in terms of concentration, we are not doing a fantastic job. Okay, so if you just use the ADE equation and you predict this, it's not going to do a great job in terms of concentrations. But here's another way to look at the problem. So this is from Freiberg 1986. And here on the x-axis, we have time. That shows also the length of the experiment, around 3 years. And here we have observations of the actual, well, as estimated from the data, second moments. And we see that within the observational error and uncertainty, it's roughly a straight line, okay? So we see that the second moment increases approximately linearly. Okay, now, what does this mean? It means that this is consistent macroscopically with the ADE model. Also, the velocity, if you look at the velocity, the effective velocity of the centroid, it is also constant. That means that the location of the centroid moves with time in a straight line. Okay, so these are consistent with the ADE. And what does this mean? It means that if you are going to be using the ADE model, for this case, this model is going to do a good job for macroscopic features, but not for concentrations. Okay, so the fact that this model works well for macroscopic is very promising, and you're going to get some reasonable concentrations, but don't expect particularly accurate concentrations. A lot of practitioners are disappointed when they see the results from the ADE model, even in this case where we claim that the ADE model macroscopically works. Okay, now, the actual plume is not Gaussian. Should we be concerned? Actually, real plumes are never Gaussian. And this is something you can take for certain. If you're going to take one thing out of this seminar, is that a real plume can never be Gaussian. And why is that? Well, because the stirring, essentially, that occurs due to the heterogeneity creates non-uniformities and makes the concentration more irregular. So essentially, you have two mechanisms. One is the velocity that tends to make things more irregular, and then diffusion is playing a catch-up game and trying to smooth things out. Okay, so let me show you a kind of home experiment. Okay, so let's imagine that we are all, first of all, familiar with the idea of stirring, right? We put some sugar in our tea, and then we use a spoon to stir it. At the end, this speeds up the mixing, but in the short term, it creates irregularity, okay? Okay, so like here, for example, we have this dye. Now, if I put a spoon, it will make it even more irregular, okay? So it creates more irregularities. All right, so the idea is that in groundwater, the same thing happens, except that the spoon is not moving while the fluid is moving. The relative motion, though, is still the same. So real plumes cannot be Gaussian, but macroscopically, they can be described as such as long as you look at macroscopic features like the centroid, the mean rate of spreading. Okay, so that's where one should focus. Now, how about the made side? That's where a lot of people, actually a lot of people missed that even in the Borden side, the plume was not Gaussian. They took it for granted. Somebody said, oh, the ADE works, so they consider they should be Gaussian. At the made side, they figured, oh my God, it doesn't look Gaussian at all. So the result is that there was a lot of disappointment about the ADE model at the made side. Now let's look at the made side. So first of all, the requirements for Fickian. The first one is stationarity. No, we don't have stationarity. It's doubtful. In fact, if you look at the geology, there are significant large-scale trends. The area where the injection happened was a low conductivity. Further out, the conductivity was much bigger. These are macroscopic kind of large-scale trends. Means stationarity is doubtful in this case. Enough time to forget initial conditions? Well, I would say definitely not. I mean, this experiment, if you wanted to reach something like Fickian, would have to run for, I don't know, 30 years. But the problem with field experiments is the budgets, of course. We have finite budgets, and definitely we cannot be there for 30 years. A lot of experiments, actually, they are started and done within a few months. And you say, but wait a minute, the relaxation time in this case is a year. So, and you finished within 3 months. Obviously, these are, well, very time-dependent results. And that's for advection domination. My view is that it's very unlikely. There are inclusions of low conductivity material like clay, and once something gets there, it takes years to get out. So how good is the ADE that a lot of people still are struggling with? In the field applications for relatively homogeneous media, I would say it works. Provided that you give it enough time, and also it works for macroscopic features. If you are interested in finding the mean velocity of the plume and the rate of spreading. But if you try to predict concentration, especially at the edges of the plume, you're gonna be disappointed. And for field applications in highly heterogeneous media, I would say not so great, okay? So here is a plot that shows all the possibilities, actually. Okay, so in this, let's say that somehow you want to get a model that is using the same parameters for the whole formation, just like the AD. What are the possibilities? Well, one possibility, of course, is the AD model, but there are many others. And I have shown a three-dimensional kind of plot in which at the origin sits the textbook AD model. But first of all, in this direction, okay, so in this direction, we may have ultimately Fickian, but pre-asymptotic. In other words, if we wait long enough, it will become Fickian, but we are still remembering the initial conditions, so it's not yet Fickian. We call that pre-asymptotic. Now, in this direction, the vertical direction is what parameterization to use. Should it be Scheidegger? We saw Scheidegger, we saw Taylor-Harris, and we could have something in between. In the third direction is anomalous. I haven't talked at all about anomalous. There is not enough time. But the idea is that in anomalous means that even the macroscopic features and even at large times are not going to be consistent with the ADE. In other words, for example, just to keep things simple, the ADE predicts that the second moment increases linearly with time. Well, an anomalous dispersion model may predict that it increases with t to the 1/2 or t to the 1.2 or whatever. Okay, I'm oversimplifying, but the idea is that it's not going to get to ADE, not even at large times. Now I'm showing another model that is widely used, is the dual domain mass transport model. It's widely used, and people often say, oh, I don't like the ADE, so I'm using the DDMT model, the dual domain. But the dual domain is actually pre-asymptotic Fickian. So if you give it enough time, it will become Fickian. But it does not use Scheidegger necessarily. The parameterization for dispersion is a combination of Scheidegger and Taylor-Harris. And in fact, there have been a study in which they only had the Taylor-Harris. All right, so that gives you an idea. And my point is that the single domain models, they are appealing, they are easy, and so on. They sound like a great thing to work on, but don't hope for very accurate predictions of concentration. Now, a different approach is based on the discretization of the domain into blocks. And now we're getting into a different. I realize we don't have much time. This is an old approach, but it has not been applied correctly, in my view. Because quite often, you see people who take a domain that they model as homogeneous and they discretize. So they discretize, but still a homogeneous domain. What we need is a meticulous consideration of how to collect data that resolves some of the heterogeneity, and then how to process data, which involves a combination of data science, computational science, and an understanding of scale issues. Okay, so part of the heterogeneity is dealt with varying properties from block to block. And all we need to do is define dispersion at the block scale. So the requirement of large scale stationarity is not there. And the relaxation times are short. Instead of being many years, it may be a week or a month. So at a small scale, we can approximate dispersion through the Fickian model with all its advantages. Now let's see a case from Lee et al. This is your Professor Lee. Okay, so essentially we have 3 cases, 3 blocks, and we would like to replace the heterogeneous block by effective properties, a mean velocity and the dispersion coefficient, for example, a longitudinal dispersion, then a transverse. And we see 3 types of heterogeneity. Okay, so the idea is that the yellow is the background, which let's assume is coarse sand or something like this. And you have inclusions that are low permeability. And we have different shapes or formation shapes, inclusion shapes, I mean. And we also have different contrasts. So the problem is we want to replace the highly detailed description with a homogeneous block that is equally good in terms of describing solute concentration at the grid scale. So if you want to represent concentration at the grid scale, this is perfect. So we want to define block dispersion coefficients. So we will show results, computational results, of apparent macrodispersivity rendered dimensionless, and the hydrodynamic dispersion is divided by mean velocity and the length. Now we chose for convenience 1 millimeter. Now if we get an effective or apparent macrodispersivity that is constant, that indicates Scheidegger. So we see the results here. So on the x-axis, we have essentially a Pechle. So a Pechle is like a velocity. So think of it as we start from a low velocity and we go to a high velocity. It's a dimensionless form of the velocity. And I will point out that we are primarily interested in values between 1 and 1,000. All right. Okay, so essentially, we see that if we are in the first 2 cases of unstructured variability, rather quickly, the apparent dispersivity tends to a constant, which means what? Scheidegger is good. The Scheidegger parameterization is pretty good. So I mean, the range where I'm interested, well, I could say effective dispersivity is constant. Okay, Scheidegger is good. But if we go now to the other case, the long inclusions and large contrast, we see that it does not become constant until very late. And the difference between here and here is 1 order of magnitude. Okay, so you have a effective dispersivity that is 10 times bigger than here, and another, almost 10 times from here to here. So clearly the Scheidegger parameterization is not that great. And actually the parameterization that I showed you, the third case, fits this rather well. All right, so what is the point? The point is that if we decide to go with block dispersivities, we may be cautious about using the Scheidegger parameterization. It's good in some cases, but actual media are highly structured. And in fact, I would say that these cases are just a first step toward realism. I mean, I'm not claiming that they're realistic, but they are moving in that direction. And if you take an actual formation and take all the structure in, I think the results would be more prominent, the difference in the effective dispersivity as the velocity increases. Okay, so some remarks to finish. I hope by now you appreciate why predicting solute transport is so hard. Dispersion is an important phenomenon, and its modeling is one of the challenges we have in solute transport. Hole formation approaches are appropriate to predict macroscopic features, but practitioners who expect accurate concentration predictions are bound to be disappointed. I was involved in one case in which I had to, I noticed that. Okay, so more accurate predictions require a different paradigm founded on resolving part of heterogeneity and using good methods to assign block dispersivities and other parameters. And that is the end of the lecture slides, and I'm ready for questions.
Okay. See. Thank you so much for the great talk. And so we didn't have a question yet, but if you have any question about the Kitanidis material, I guess you can speak up, or so probably. Yeah, I have one question. So you mentioned about during the talk, you mentioned mixing and dilution. So maybe some students who are not very familiar with this transport phenomena, could you actually tell the difference and similarity of these two terms that is used in the hydrology or geology community?
Yeah, I mean, for many people, spreading and dilution go together. This is based on the thinking along the lines of a Gaussian model, for example. If you have more spreading, you have more dilution. That is only approximately true. What happens is, actually, in the long term, they will be the same. But in the short term, here's what happens. You have a plume, and then it starts spreading, but the dilution is slower. In other words, the peak value does not go down as quickly as, let's say, one would have expected from the spreading. Okay, so you have spreading, and then you have dilution. It lags the spreading. Okay, so first spreading, then dilution. Dilution means what? Dilution means that the same mass is being spread over a bigger volume. Now, velocity itself will distort the isoconcentration lines, but it will not change the concentration values. It is diffusion that will do that job, and diffusion is slow. And so first, everything has to be distorted a lot, and then diffusion becomes important because you have local gradients that are important, large, and diffusion becomes important. So that's why there is a lag between spreading. You can have a plume that has spread a lot, but it has not diluted a lot. In other words, the peak concentration and other measures of dilution have not changed that much. Okay, I don't know if that is what you wanted.
Okay, thank you.
I have actually a follow-up kind of question. Thank you so much for the wonderful presentation, and you actually addressed the one of the most fundamental issues that the engineer should know on top of Gaussian diffusion. And so I actually have a lot of questions, but the single question is converging to what is the primary factor that the Gaussian diffusion is failing?
What is the primary what?
Primary factor or reason that the normal diffusion or Gaussian diffusion is failing?
Is failing. Well, the primary reason is that you have heterogeneity in velocities.
Okay.
So because you have heterogeneity in velocities, even if you start, let's say that somehow you manage to have an initial condition that is a Gaussian distribution.
Yes. Yeah.
Now, immediately the velocity is going to start distorting it. Okay, so it starts Gaussian, but immediately it starts getting non-Gaussian because of the velocity. And it will become more and more non-Gaussian until the diffusion is becoming strong enough to slow down the process. So in a way, the velocity is the troublemaker, and the diffusion is trying to catch up. And ultimately it catches up, but it's always a little bit behind. So, and again, it has to do with the heterogeneity. It has to do with the fact that velocities are highly variable, highly non-uniform. I mean, you can imagine, let's say that you have parallel flow and you put in a Gaussian. Well, in the layer where the velocity is high, it's gonna move fast. The other is gonna stay behind. So you lose this regular shape. But sooner or later, the diffusion, because now you have significant concentration gradients, becomes important, and it starts correcting toward the Gaussian. So it's this constant fight between the distorting power of velocity and the diffusive and smoothing out power of diffusion.
Suppose you have a kind of poorly dispersed or bidispersed sphere packing as a sample porous media, then even if your the pore size is kind of poorly dispersed, but you could still see that one as the uniform porous media, because the porosity or the grain size fluctuation could be seen easily, uniform if you look at them in a larger scale. And so there are a variety of different ways to make this diffusion phenomena explained better way. So for example, like Levy flight or Ito-Wiener process in anomalous diffusion. But I still think that the diffusion process that we are looking at, it still depends on the size of the sample that we look into.
The scale of the problem, in other words.
Yeah.
No, I agree fully. Yeah, I mean, a lot depends on the scale of the problem. I mean, we showed that if you look at the very macroscopic concentration in a stationary medium with enough time, that the ADE works. But it's only in terms of the macroscopic. So if you're interested in the macroscopic, and in fact, in the stochastic theories, they talk about the ensemble average concentration, right?
Yeah.
Now, the ensemble average concentration is Gaussian, but not the actual concentration, right?
Right, yeah.
Yeah.
Well, thank you.
Okay, we have one question from audience, from Paul Erie. So he said, does dispersion and diffusion have much more effect on the perimeter of plume, or do they have similar effect throughout the over the plume? So that's the question.
Yeah, I mean, the diffusion process is more important at the edges. That's where you have the biggest differences, let's say the biggest gradients. If you are right in the center of the plume, diffusion is less important because the gradients, the average gradient is small. A couple of students of Gelhardt have looked into this, and basically it turns out that the mean, sort of mean gradient is what matters. Okay, so yeah, I mean, I would say toward the edges of the plume, but not quite at the very edge where nothing is happening, but toward the edges of the plume, diffusion is playing a more significant role.
Peter,
Ali, yeah.
Yeah, I guess my question is about field applications. You described a great concept about block dispersivity, but if we want to apply this in the field scale, I guess we have the issue of measurements, that we can really satisfy the small scale measurements.
Yes, absolutely. I mean, that is the main issue why people, even though they say, oh, I don't like the ADE, I don't like this, but at the end they go back to the same models because they go to an actual case in the field, let's say a consulting job, and they say, oh my God, I only have a few measurements. I mean, I'm not gonna resolve the heterogeneity. I don't have that. So let's assume that we have a certain mean velocity for the whole domain, and we have a mean and an effective dispersion for the whole domain. Okay, so, but the point is that in many applications, let's say I have been involved in cases where they have been studying the same site for 20 years, making very little progress. But if you tell them, look, if you spend, let's say, $200,000, $300,000 doing geophysical and hydraulic tomography methods, you will resolve a lot of the variability. And they say, oh, but $200,000 is a lot of money. Well, you have spent, you know, 4 million by now, 5 million, and you have not made any progress. So the thing is that it's not going to be easy. If you go to an actual site, you have to tell them, look, you want accuracy? It will cost money. You will have to do some additional studies of collecting a lot of data. They will cost money in the range of hundreds of thousands of dollars. I mean, we had one case a few years ago that we did it for a company, Syndial, and essentially they were interested in our tomographic methods, and we did in Cagliari. So we did hydraulic tomography, and we were able to resolve heterogeneity at significant scale, at significant detail. I mean, it costed them something like, including the research that they supported, it costed them something like $150,000, $200,000. But we resolved heterogeneity over the area that they were interested in. Okay, so it's possible, except that it requires a different way of thinking and the willingness to spend money. Usually what happens is if you tell them you need to do this study and it will cost $300,000, it sounds like a lot of money. But 10 years later, after they have spent much more, they realize that they should have spent this money. I don't know if it answers.
Yeah, thanks. But I think the scale in Hawaii is very large in terms of aquifer sizes.
Sure, but again, in that case, you're not, again, it's true. But large problems, You don't need to resolve the small scale features. I mean, you have to define at what scale you need to resolve heterogeneity. And also, you know, if it is, Hawaii is a large, you know, the island is large and you have a lot of measurements though, you can do some kind of inverse modeling to try to figure out what heterogeneity you may have. Again, obviously, there is not one solution for all problems, but all I'm saying is that it depends on the scale of the problem. Usually, if you have a large-scale problem, you also have large-scale measurements, and you are interested in large-scale features and not details. Okay, so, but the usual answer, unfortunately, the easy way is to say, okay, I'll assume it's all homogeneous and it has one effective velocity and one effective dispersion. And then the question is, what effective dispersion? Is it going to be Fickian? Is it going to be anomalous and so on? But at the end, I feel that none of those are going to give satisfactory answers. None. Okay, and of course, some of the best minds are working on very interesting methods, but at the end, are they going to be predicting concentrations? Only macroscopic features. And the practitioner may be disappointed when they say, oh, this doesn't predict the concentration.
Okay. Okay. Another question from audience, from Monica from Germany. So, if the dispersivity depends on the property of medium, and she asks about how heterogeneous can be, you know, highly heterogeneous aquifer. So, do you have any kind of idea of the magnitude?
Yeah, I feel that realistic situations with large heterogeneity will not satisfy the Scheidegger, except approximately. Okay, so why? Because it's a combination not just of heterogeneity, but also of structure. If you have a lot of parallel features, if you have inclusions that are long and very low conductivity, as it often happens, you have sometimes, you know, lamina of clay. They are relatively thin and long, but the conductivity is extremely low. And also the diffusion in clay layers is low. Okay, so what happens is mass transfer now is going to be important. And also, so it's not just a matter of the variance. I would say once you get to variances like 4 and 5, just like in MADE, I start being suspicious of Scheidegger. But also I have to look at the structure, okay, the structure, because we saw in the slides that if you even if you have tremendous variance, if it is unstructured, you know, inclusions like here. Okay, so here we have inclusions that are, you have a very large variance, right? But Scheidegger is very good. Okay, why? Because there is no structure. But here, same variance, Scheidegger is not as good. Okay, so it's not just the variance, it's also the structure. But you know, the issue of structure has not been addressed sufficiently. For example, I see cases where people say we did a very sophisticated modeling, and then they have blocks, let's say, that are a few meters in every dimension, and they represent them as isotropic. Now, I find it extremely difficult to believe that there is anything at that scale of a block that is isotropic, because the geology is always so, you know, so structured. Okay, so there are a lot of things to do in that area.
Okay. Oh yeah. Yeah, thank you so much for all the answers. You know, yeah. So probably we are just 10 minutes late, so we can wrap up here. And so thank you so much, Peter, about
My pleasure. Thank you for the invitation.
Yeah, definitely we'll have another chance, to invite you here, probably after the pandemic.
Okay, thank you.
Okay.